Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Muhammad Tahir. In these videos, we are discussing the direct design method. In the last video, we discussed the procedure of direct design method. We have covered the first 6 steps of the direct design method. In this video, we will see how we can distribute this static movement m0 into longitudinal direction, transverse direction and vertical direction based on the coefficients provided in the ACI 318 code. So first of all, the division of total panel moment m0 into negative and positive moment for interior span. For interior span, this distribution is just like this, because in interior span we have continuity on both the side of the slab, on both side of the panel. So in that case, these negative moment will be identical and this will be 0.35. So 0.65 plus 0.35, it will be equal to 1. So the total moment, this one will be m0. So this is for interior spans. For exterior span, this scenario will be different. It will be based on the end condition. So for end span, we can select this negative moment based on this table. So exterior edge unrestrained. If the exterior edge of the beam, for example, this is the frame and this exterior edge is unrestrained. So in that case, interior negative moment will be 0.75 at this port, positive moment at the center will be 0.63 and at this port moment will be 0. As we know, at unrestrained port the bending moment is 0. So here the bending moment will be 0, positive moment will be 0.63 times m0 and this one will be 0.75 times m0, like this. Here bending moment will be 0, here positive and here negative. So here the pictures are drawn. So this is the similar case as that of column 1. Exterior edge unrestrained. Here the bending moment is 0, here 0.63 m0 and here it is 0.75 m0. And the second column is for slab with beams between all supports. So if the beams exist between all support, interior as well as exterior, in that case the interior negative moment will be 0.7, positive moment will be 0.57 and exterior negative moment will be 0.16. This one will be the case. 0.6, 0.16, 0.57 and 0.70 m0. So this will be the distribution of static moment. Okay, if there is slab without beams between interior support, if there are no interior beams but we have edge beam, in that case the distribution will be 0.7, 0.5 and 0.3. This one, no interior beam but we have edge beam, and if there is no edge beam, in that case it will be 0.7, 0.52 and 0.26. This one, this case will prevail. So we have to an exterior edge fully restrained, so it will be just like the interior panel. So it is similar to the interior panel, because here the both ends are fully restrained, the bending moment on both edges will be same. Okay, so based on the end conditions we can decide the case, and correspondingly we can calculate the bending moments at exterior support, at the center, and at the interior support. And this is for end span. Okay, here is one note that the critical section for negative moment shall be at the face of the rectangular support. So we need to calculate the negative moment at the face of the support, not at the center. Okay, negative mu shall be the greater of the two interior negative moments calculated for spans framing into a common support unless an analysis is made to distribute the unbalanced moment in accordance with stiffness of adjoining moment. So here we can see that at this support the bending moment are different. On this side the interior negative moment is larger, and on this, from this panel, the moment is small. So for this support we will consider the larger value. So larger value out of these two will be considered as a design moment. Okay, next is distribution of factor negative and positive moments. So once we have calculated these moments, positive moment, negative moment, and negative moment. Negative, positive, and negative. The next step is to distribute it in this direction, in transverse direction, to column strip and middle strip. So let's see how we can distribute in the transverse direction. So the distribution of factor negative moment and positive moment to the column strip for interior negative moment. So the interior negative moment can be distributed to the column strip by using this table. So here this table have two factors, the stiffness ratio of beam and the aspect ratio of the slab panel. So based on these two values we can select the factor. For example, so this is interior negative moment, for example at this point. Sorry, we are considering the other direction at this point. This is exterior negative, here positive and negative if we are considering this frame. So this one will be distributed on column strip and middle strip. So if alpha f L2 over L1 is 0, it means the stiffness ratio of beam is 0. No beam exists. And the aspect ratio of the slab panel is, for example, 1. The panel is square. So in that case, 75% of this negative moment will be resisted by the column strip, and the remaining 25% will be resisted by the middle strip. So 75% moment will be transferred to the column strip, and the remaining 25% will automatically go to the middle strip. So this is, for example, column strip, and this interior negative moment at this spot, so 75% will be resisted by the middle strip and 25% will be resisted by the middle strip and 75% by the column strip, this negative moment. So this is for column strip for interior negative moment. So based on these two factors, we will consider the coefficient from this table, and then we can calculate the bending moments for column and middle strip. Okay, from here we can see we have only 0 and 1 value, 0.5, 1 and 2. So in between values we can interpolate the value. Okay, next is division of factor negative and positive moments to the column strip for exterior negative moment. The previous was interior negative moment and at the interior support, and here it is for exterior negative moment. For exterior negative moment, the distribution is based on 3 factors instead of 2. This flexural stiffness ratio, aspect ratio plus torsional stiffness ratio. So the distribution of this negative moment to the column strip and middle strip is based on these 3 factors. For example, if we have a slab system without interior and exterior beam, without edge beams, so in that case flexural stiffness ratio will be 0. Similarly, torsional stiffness ratio will also be 0, and if the panel is square, aspect ratio is 1, so in that case this coefficient will be 1. So complete negative moment will be resisted by the column strip. 0 moment will go to the middle strip. 100% negative moment of exterior support will be resisted by the column strip. So again we can interpolate the values if the alpha, f, beta r aspect ratio is in between the given values, or otherwise we can use this expression. We can use this expression to determine the contribution of column strip. So the moment resisted by the column strip can be calculated by using this formula. Okay, next is division of factor negative and positive moment. So the column strip for positive moment. In the previous slides, we have discussed the negative moment of interior support, negative moment of exterior support. Now the positive moment, how we can distribute this positive moment to column strip and middle strip. So again it is based on these 2 factors. So for example, again if there is no edge beam or no beam in between the columns and the aspect ratio of the column is 1. So in that case 60% of the moment will be resisted by the column strip, this one, and the remaining will be resisted by the middle strip. And if the aspect ratio is 0.5, so in that case again 60% will be resisted by the column strip and remaining will be resisted by the middle strip. 60% of this positive moment. Okay, so division of negative and positive moment to the middle strip. So once we have determined the contribution of this column strip for exterior negative, interior negative and positive moment, then we can easily calculate the contribution of middle strip. For example, as we have seen in the previous slide, that positive moment will be resisted by this column strip equal to 0.6 times M positive, means 60% of M positive will be resisted by column strip. Then the remaining 40% will be resisted by this middle strip, half middle strip or middle strip. So the portion of negative and positive factor moment resisted by the column strip shall be proportionately assigned to the corresponding half middle strip. So the moment not resisted by the column strip shall be proportionately assigned to the corresponding half middle strip. Okay, here it is a very important thing to note. This word proportionately assigned to the corresponding half middle strip. For example, we have this frame and this is the column strip. If it is an interior frame, we have half middle strip on this side and half middle strip on this side. If the width of middle strip on this side is, for example, 2 meter and on this side it is 1.5 meter, and out of the, for example, this positive moment, 60% is resisted by the column strip. So the remaining 40%, 0.4 times m positive, will be resisted by these two middle strip. Okay, so the question is, either we will divide it by 2 and assign the half portion to this middle strip and half portion to this middle strip. It's not like that. We have to distribute this moment proportionately to this middle strip and this middle strip based on their width. So the overall width is 3.5 meter and the width of this is 2. So 2 by 3.5 times 0.4 m positive. This will be resisted by this middle strip, and for this middle strip it will be 1.5 divided by 3.5 multiplied by 0.4 times m positive. So we have to consider their proportion based on their width on each side or for each half middle strip. Okay, each middle strip shall resist the sum of moments assigned to it to its two half middle strips. Actually, here we have one half middle strip, this one, and the other half middle strip, this one. So for this middle strip, half middle strip, the moment will be from this frame, and for this half middle strip, the moment will be from this frame. So m of this, for example, it is m1, and m from this m2. So the sum of these two will be the total moment for middle strip, for complete middle strip. Okay, next is vertical distribution. So in vertical distribution, division of column strip moment to column strip slab and beam. So actually this is total column strip, and we have calculated the total moment for this portion, which includes beam as well as slab. So we have to separate the proportion of beam and slab. So the portion of column strip mu in beam, how much it will be? It will be based on this factor. If there is no beam, so the zero contribution from this beam. And if the stiffness ratio is greater than 1, then 85% of this total column strip moment will be resisted by beam, and the remaining 15% will be resisted by slab, this portion. 15% by slab and 85% by beam if the stiffness ratio is more than 1. And for in between stiffness ratio, we can interpolate between these two values. So this is vertical distribution. In the last slide, in the distribution of exterior negative moment, we have one factor beta T. This beta T is actually torsional stiffness ratio. The question is how we can calculate this beta T. So the torsional member is at the edges. So for these edge beams, we need to calculate this torsional stiffness ratio to distribute this exterior negative moment to column strip. In the next video, inshallah, we will cover this portion, the calculation of torsional stiffness ratio. We will see what is torsional stiffness ratio and how we can calculate it.